Next, we're going to introduce the concept of spectrum for continuous time periodic signals. Already showed that this is the Fourier series for a continuous time periodic signal, and its coefficients in here can be calculated using this integral. And we define this is the forward continuous time Fourier series, while the other equation is called the inverse continuous time Fourier series. If we expand the inverse continuous time Fourier series, it can be written as infinite number of terms in here. And those terms, they all have specific names. The first one is called the direct current component, DC component. And these two terms, n equal to -1 and +1, they both called the first harmonic or the fundamental frequency component. While for the other terms, for example, when n equal to capital N, either negative or positive, they both called nth harmonics. So these are all the different harmonics, and the summation of all the harmonics and the DC components will become the original periodic signal in the time domain. And the C sub n, we introduce is the coefficients in the Fourier series, is actually defined as the spectrum of the original signal x of t in the time domain. And these two signals, x of t and c sub n, they are a pair of Fourier series for continuous time periodic signal, and they are in one-to-one correspondence. So basically, when you know x of t, then automatically you know c sub n through this equation. Or the other way around, if you know the signal's spectrum, c of n, then automatically you know the signal's original form in the time domain through this summation. And we define this is the Fourier spectrum. And in general, the spectrum is a complex function. So when I say it's a complex function, it can be broken into two independent parts. And the first one represents the amplitude or magnitude of the complex function, while this part is the phase of the complex function. So we also gave their specific names. The first one is the amplitude spectrum of the signal x of t, and this phase term is called the phase spectrum of the original signal x of t. Here we try to show some examples how we can evaluate a given signal's spectrum based on the definition. So this is a periodic continuous time signal. How can we calculate that signal's spectrum? Well, based on the definition of continuous time Fourier series and the definition of the original signal in the time domain, we can plug the definition of the signal into the definition of the Fourier series. And without going through the details, we show you the integral is equal to this function. And we can simplify it using sampling function. And this is a more compact form of the spectrum of the periodic rectangle signal. And we may show its waveform in the frequency domain. Pay attention to the waveform in the frequency domain. It's a discrete spectral lines in there. And here is the mathematical expression of this plot. In the second example, how can we evaluate the spectrum of this periodic triangle signal? Again, we can use the same technique. We just plug the definition of the periodic signal into the definition of spectrum. And this is quite straightforward. So without going through the details, the spectrum actually is in this format. And we can again plot it in the frequency domain. Again, for periodic signals in the time domain, the spectrum in the frequency domain is discrete spectral lines. And if we put these two examples together, we see that for that original signal in the time domain, this is the spectrum in the frequency domain. And for the original signal in time domain like that, this is the spectrum in the frequency domain. We want to emphasize that the signals in the time domain and its spectrum in the frequency domain, they are in one-to-one correspondence. In one-to-one correspondence. There's another example, how we can use the definition to simplify the calculation. So the question here is, how can we calculate the spectrum of the signal shown in here? And the mathematical expression of that signal is two terms of cosine functions. So instead of using the definition of the forward continuous time Fourier series, we can also use the inverse continuous time Fourier series to find out the coefficient C sub n or the spectrum. So we can use Euler equation to represent the original signal using imaginary exponential signals. And then by definition of the inverse continuous time Fourier series, we understand that these and these are the Cn's, so that we can figure out Cn, n equal to 1, -1, 3, and -3 are equal to these specific coefficients. So based on this, we understand, we'll already get the Fourier transform or the Fourier spectrum of the given signal here. And the plot of the spectrum will look like this. So this is based on the inverse continuous time Fourier series to help us figure out the spectrum of the signal in the frequency domain. And this signal or this spectrum, they are complex spectrum. So there's two independent components. One is the amplitude spectrum, while the other one is the phase spectrum. Here's another example. How can we, because we say that the time domain and the frequency domain, they are in one-to-one correspondence, then if you are given the spectrum of a signal, then we should be able to figure out the signals in the time domain. So here is the spectrum. Then how can we figure out the original signal in the time domain? What we can do is we can use the definition, the inverse continuous time Fourier transform, to figure out what is the original signal in the time domain. So we just plug this definition into the inverse continuous time Fourier series. We're going to get the expression in the time domain like this. It's quite straightforward. So in these examples, we show you guys how to use the forward continuous time Fourier series and the inverse continuous time Fourier series to figure out either the spectrum or the original signals in the time domain. There are some important characteristics of the Fourier series we need to understand. Now we take the periodic rectangle signal as one example to show those characteristics. The first one is the spectrum of periodic signals in the frequency domain composed of a series of spectral lines, and the interval between the lines is equal to omega sub none, which is 2 pi over t sub none, the period of the original signal in the time domain. The second characteristic is for any periodic signals with bounded amplitude, the amplitude or the magnitude of the spectrum in general is decaying. In other words, the amplitude is getting smaller and smaller, approaching to 0. The third is specific for periodic rectangle signals. We can identify that in a range between 0 and 2 pi over tau. In this range, the majority power of the signal actually happen in that region. So this is called effective bandwidth, omega sub capital B, which is equal to 2 pi over tau. And tau is equal to the duration of the periodic rectangle signal in the time domain. And we can observe that the effective bandwidth, omega sub capital B, is inversely proportional to the duration of the signal in the time domain tau. Next, we're going to introduce a specific phenomenon called Gibbs phenomenon. We already learned that this is the Fourier series decomposition for any periodic continuous time signal. And these will equal to each other if the number of terms goes to infinity. But what if we have only limited number of terms, harmonics, in here? So we're going to try to use this equation, try to synthesize the signal, the original signal, use this one to approximate it and do the comparison to see what's going to happen. So using this equation, and we again take the periodic rectangle signal as one example. When the number of harmonics is equal to 5, then this will be the synthesized signal. What if we increase the number of harmonics? For example, if we increase the harmonics up to 500, you're going to see that although the wiggling in here is getting smaller, but the amplitude of the overshot in here is in the same magnitude. So this overshot happens only at the discontinuity point in here. And the percentage of the overshot will not change, even if you change the number of harmonics. And this overshot will not go away unless the n is equal to an infinite number. So this phenomenon was first explained by this scientist. Therefore, the phenomenon is named after him. Thank you.